Okay, perfect. So thank you for this time, to this occasion to present my work. So I will talk about a novel propulsion method for underwater autonomous vehicles that only requires internal actuators and actually not any external actuators like propeller, etc. So classic common AUV design typically relies on external actuators such as propeller thrusters or actuated fins, ballast, etc. And it is very useful, but brings limiting constraints in the design, such as wear and tear due to the high salinity, for example, of seawater. It is also subject to the depth, and when increased depth, it becomes more and more difficult to design these actuators. Sometimes it also brings constraints of dynamic water tightness, which can be difficult to manage. And it increases the bulk of the entire system. So in many environments, it is not critical, but in some, it can become so. So, for example, for great depth scenario or constrained environments such as kelp forest. So the question I'm trying to answer is, would it be possible to design a fully a propulsive method that does not require any actuators in the water? So my solution was to use two existing technologies. The first technology is the use of the control moment gyroscope and the flexible fin. So I'm going to present more in detail both of these solutions. So the first one, the control moment gyroscopes, is mainly used in two fields. The first one, the principal one, is in space. So for satellite orientation. So the CMG, control moment gyroscope, consists in a flywheel rotating at a constant speed. Commonly, it's spinning at a very high speed. And a second motor, called the gimbal motor, that oscillates the flywheel. And the oscillation creates a gyroscopic torque. The flywheel generates a gyroscopic torque that applies on the whole system. So the main application is satellite orientation. It is also used for ship stabilization to fight the roll of the ships. But it is not used typically for propulsion. The second solution is the second technology is the flexible fin. So it is bio-inspired by sea creatures such as fishes, whales, or even so not really bio-inspired, but it is like a human the fins of human divers, and it simply generates thrust when it's being oscillated, actuated. So there are many papers and work on this, such as the UCAT in Tallinn University, that creates a fully autonomous AUV using fins, flexible fins. And there are many more examples, bio-inspired or bio-mimetic. And so the prototype to demonstrate a fully internal propulsive method combines these two technologies by enclosing in a fully sealed tube two control moment gyroscopes. I will explain why I use two. And a flexible fin that is attached to the rear of the tube.
But we saw only the slide 2.
Ah, okay. I will try to share it again. Sorry. Okay, maybe I will. Okay.
Reshare, yes.
I will try a simple method.
Ah, yes.
Okay, I don't think this will. Well, sorry, this is a present view, but this will be simpler.
Okay.
So yes, this was a moment interesting. So the prototype I made to demonstrate this propulsive method without any external actuators combines the first technology, the control moment gyroscopes, two of them actually. I will explain why, and the flexible fin that is attached to the rear of the tube. And it is attached via a flexible hinge to mimic a flexible fin. And so there is no motor outside. So to understand better the dynamics behind the gyroscopic torque, one can use the Ehlers equation for a rigid body. So I'll not dig into the details. But what's interesting is that we obtain a gyroscopic torque that is proportional to both the spinning speed of the flywheel and the oscillation speed of the gimbal of the servo motor. So by oscillating the servo motors, so delta dot, we generate an oscillating torque on the system. But you can see that the gyroscopic torque is created on the flywheel frame. So when it is oscillating, it also creates a torque on the x0 axis. So it creates a roll on the robots, which is not desired. And this is why there is two CMG. By setting two CMGs, spinning them in opposite direction, and making them oscillate in symmetry. The sum of the torque on the y-axis cancels out, and we only keep the torque on the z-axis to only keep the torque that is desired to make the fin oscillate behind. So the dynamics between the flexible fin is actually based on a lift and drag model. So this is a rigid plane with a flexible hinge joint. So it's pretty straightforward to model. I didn't dig into soft robotics. And by combining these two dynamics, we can simulate the behavior of a robot in a numerical simulation. So the signal on the top right you're seeing is the angle of the servo motors, the gimbals, and the plot on the top on the second plot is the torque generated. So the robot oscillates the fin follows and creates thrust to propel itself through the water. An interesting thing we can see in simulation that will later be confirmed is instead of using a symmetrical triangle wave, we can use asymmetrical triangle wave to create an uneven to break the balance and control our heading. So the prototype was used to make an experimentation and confirm the simulated behavior. So what you're seeing is the two CMGs being oscillated at in symmetry. And next, there will be a side-to-side comparison between the simulation and its behavior in the pool at ENSTA. And so it shows satisfying behavior with settings close to the real prototype. So this is the work I've been doing for an iOS submission. And next, with our intern, we will try to make it a fully capable AUV, capable to be controlled in a 3 dimension in our pool. So thank you for your attention. And if you have any question, I would be more than happy to try and answer them.
Is there any question for Gabriel? Well, I have one.
Yes.
So your robot for now, it has been designed to only move in 2D, or do you already have everything required, like mechatronically speaking, that is ready to move to 3D?
No, actually, with this system, it is only capable of moving in the 2D plane.
Okay.
And so the next step, if we want to keep a fully internal propulsion method, we could, for example, add a sliding mass inside the tube for it to be able to control the tilt and dive in the water. But actually, with this system, it's only possible to move in the 2D plane, yes.
Okay. And in terms of fins, would you add an extra fin maybe when moving to 3D, or?
Actually, I don't think so. We'll keep the fin, and with the sliding mass, we will be able to tilt the 2D plane we are controlling the robot in. So only tilting forward and oscillating to dive.
Okay, thank you for your answers.
Thanks.
I see a question from Alessandro.
I will look.
It's not really Alessandro, it's Gabriel. But I was wondering in a twofold. I have twofold question. My first is like, have you tried to evaluate the efficiency of your propulsion device? And my second one is like, have you tried to compare to other non-moving part or non-rusting parts propulsion system like magneto-hydrodynamic drive?
So thanks for the question. Actually, currently we're not measuring the efficiency. It was more of a prototype to demonstrate the feasibility. But it's really an interesting question, and maybe in the future work, yes, we try to compare it to other similar method. in terms of efficiency, in terms of maximum speed or controllability. And now actually I saw, yes, some solution with internal magnets, but I did not try for a moment to compare it to this solution.
But it's a very cool design what you have. Thank you for your presentation.
Thanks for the question.
Is there anyone else? Otherwise, we can move to the next presentation.
I see a question, a written question.
Oh yes, there's one in the chat. Jalil, would you like to ask your question orally?
Yes, can you hear me?
Yeah.
Yes, I can.
Okay. My question is, how I computed the common laws for the gyroscope torque to control in order to control the robot, and do you use trajectories to know how to move it and to make it linked with the back of the robot, the thing which correct the trajectories?
Yes. So the back of the robot, the fins, is not controlled at all. It is completely passive. And so to be able to control the robot in a 2D plane, we try and compute the gyroscopic torque created by the flywheels. So actually, we have not made an optimal efficiency-wise an optimal control. This has not been the subject of the work, but we are able to compute the torque created by the flywheels, and how to say it? Well, it's more like an empirical control for the moment.
Okay, so for the example, you just made the robot go forwards for an example showing that you were able to control it.
Yes, this is right. And with some experience, more experience, we are able to show it that there is indeed a frequency of control that optimize the thrust. But it is still empirical and not demonstrated.
Okay, and is it a goal for the future?
Yes, it would be an interesting goal to try and put everything really neatly.
Okay, thank you.
Thank you.
We have maybe a very last questions from the Liam RS and PhD students, or is it good for you?
Yeah, we have one question from one colleague. I have one question. Very good job. Thanks for the slides. I only have one question regarding the desired trajectory that you can follow. For example, it can be arbitrary. You can put any type of trajectory, or it's only like this type of.
So you need to keep a constraint because the gimbal. So here is the gimbal angle. What you're controlling is only delta one, the angle of the gimbal, because the spinning speed can be set, but is very slow to reach the speed. So I don't think this is a very good idea to modulate it. Sorry. So what you're controlling is delta one, and delta one need to be kept between approximately minus 0.5 minus pi and pi, because it cannot be turn in a full cycle.
Okay. And this approach can be how robust is against failure actuators? In this case, it's one actuator.
Well, as we have two CMGs, if one fails, we still can propel ourselves, because we will just have a parasite motion in the wall axis. But I made the first experiments were made with only one CMG, and it was able to propel itself through the water. So I would say if one fails, we continue.
Okay, thanks a lot.
Thanks.